Hello everyone, welcome back to the channel. This video is about the AC parallel circuits. In the previous videos, I had taken the examples of AC series circuits, and what we had seen in AC series circuits, the current through each of the circuit element that remains same, while the voltage across the different circuit elements which are connected in series, that is different. So when we move on to parallel circuits, in parallel circuits, the voltage across the elements or the branches which are connected in parallel, that remains same. So voltage is same for the elements or the branches which are connected in parallel, while the current is different. Current is different for parallelly connected elements, or we can say branches. If we are having only a single element like a resistance or an inductance or capacitance, then we can say we have a single element connected in one branch, or we can have the series combination of circuit elements and then they are connected in parallel. So basically in case of parallel circuits, we have to study that how the current is getting divided. Now when it is AC circuit, so at that time we have to consider all the currents and voltages as the phasor quantities. So for parallel circuit understanding, let's take the example of a simple parallel circuit which have a resistance connected in parallel with inductance L, and that is connected in parallel with capacitance C, and then we have a voltage source V connected over here. Now this voltage source V is written as V angle 0. Since voltage is common among these three circuit elements, so we will consider that this is our reference. Current through resistance is denoted by IR, current through inductance by IL, and through capacitance is denoted by IC. Let's say the total current supplied by this source is I. Now, over here we have a junction. Current I is incoming current, while IR, IL, and IC, they are leaving the junction. So we can say I is equals to IR plus IL plus IC. This is as per Kirchhoff's current law. So if you want to find out the value of IR, then IR will be equal to voltage across this resistance divided by resistance. So voltage across this resistance is V upon R. Then we have current through the inductor. Again, it is equal to voltage across this inductor, which is V upon the reactance of this branch. Now the reactance of this branch is JXL. Now we need to consider the phase difference. That's why it is written as JXL. And the third current IC, that is equal to voltage across the capacitance, again same as V upon the reactance of this branch. Now the reactance of this branch is minus JXC. So this is what we had already done in case of series circuit. If you haven't checked that video, you can check that, and the link for the same is available in the description box. Now when we substitute the values of all the currents in this equation, then I, which is equal to IR, we can write it as V upon R. IL is V upon JXL. IC is minus V upon Jxc. Now if you want to take this j in the numerator, then we can write this as minus j v upon xl. Now how this minus j come over here? Because j square is minus 1. So we multiplied this equation by minus j square. Minus 1 and j square is 1. So minus 1 plus 1. So that plus sign is over here. Now we can replace it by minus j square in the numerator. We have a j in denominator, so what we are left with? Minus j. Similarly, we can write this minus 1 upon j as plus j v upon xc. Now in this equation v is common. 1 by r minus j 1 by xl plus j 1 by xc. 1 by r, the inverse of resistance is conductance, which is denoted by G. 1 by XL is written as BL. 1 by XC is written as BC, where B is known as susceptance. G is conductance. So I is equals to V into Y, where Y is admittance. So admittance has two parts, real part and imaginary part. The real part represents the conductance and the imaginary part represents the susceptance. Now it's always not necessary that susceptance is simply 1 upon reactance. It can be different depending upon which elements are connected and how they are connected in the parallel circuit. To understand this, we can take another example of parallel circuits, but before that, let's draw the phasor diagram for this parallel circuit. So when we want to draw the phasor diagram, we have to select one quantity as reference quantity. Since voltage is common among all these circuit elements, so voltage is considered as reference. So we have voltage as our reference. Then we have current IR. Current IR is in same phase with voltage IR. Now in case of pure inductor, we know that current lags behind the voltage by 90 degree IL, and current through the capacitor that leads the voltage by 90 degree. This angle is 90, this one is also 90. Now IC and IL, they are in phase opposition. Now depending upon whether IC is more or IL is more, we can have two options in this phasor diagram. If IL is more than IC, then the resultant current is in same direction with the IL minus IC. And the phasor sum of this IL and IC, IL minus IC and IL will give us the value of total current I, which will be at angle phi. Since this current is lagging behind the supply voltage by angle phi, so this is a case of lagging power factor. Similarly, we can have the case when current IC is more than IL. IR will remain in same phase. IC leads the voltage by 90 degree. IL lags behind the voltage by 90 degree. IC minus IL, that will be in same phase with IL, since in this case we have considered the case when IC is more than IL. Now the resultant of these two, that is the total supply current I. So from the phasor it's clear that this current I lags behind, so it leads this voltage V by angle phi. So this is a case of leading power factor. Now let's take another parallel circuit example to understand that how the parallel circuit can have different susceptance in comparison to this one. So for that, I am considering the most common example where we have a RL branch connected in parallel with RC branch across a voltage source V. Let's say this resistance is R1, L, R2, C. This one is voltage source. V is V angle 0. Again, it's our reference. Current drawn by this branch is denoted by I1. Current drawn by RC branch is denoted by I2. And the total current drawn from the supply is I. So again, I will be phasor sum of I1 and I2. Now if we want to find out the value of I1, I1 will be voltage V upon impedance of first branch. It will be V upon Z1. And what is Z1? Z1 is R1 plus J XL. I2 is V upon Z2. Z2 is R2 minus JXC. This is same as in case of the series circuit. We had written the impedance in case of series circuit for RL branch as for RL series circuit as R1 plus JXL and for RC series circuit R minus JXC. On the similar basis, I have written the value of Z1 and Z2. We have this I as I1 plus I2. We can write it like this: V into Y1 plus V into Y2. Like it can be written as V into Y1 over here. This one is V into Y2. 1 upon Z1 is Y1, 1 upon Z2 is Y2. Now let's find out that what's the value of Z, Y1 and Y2. Y1 is 1 upon Z1, 1 upon R1 plus JXL. Now we have a complex number in the denominator. What we need to do, we need to rationalize this. For rationalizing, we will multiply by R1 minus JXL as well as divide it by R1 minus JXL. So it will become R1 minus JXL upon R1 square plus XL square, which will be equal to R1 upon R1 square plus XL square minus JXL upon R1 square plus XL square. So this real part over here actually represents a conductance. This one represents a conductance of first branch and the imaginary part represents the susceptance of first branch. So Y1 is G1 minus J B1. Now we can see that how the conductance as well as susceptance, they are different from the previous case where we had the parallel combination of pure resistance, pure inductance and pure capacitance. Similarly, we can find out the admittance of second branch Y2 as 1 upon Z2, which is R2 minus JXC. Again, we need to rationalize this. For rationalizing, we will multiply it by R2 plus JXC as well as divide by R2 plus JXC. So now what we get? We will get R2 plus JXC upon R2 square plus XC square. When we separate the real and imaginary part, it's r2 square plus xc square in the denominator plus jxc upon r2 square plus xc square. So this real part, it represents the conductance of second branch, and this xc upon r2 plus xc square, that represents the susceptance of second branch. So this is how the susceptance and conductance, they are different. So total admittance Y, here we had written that I is equals to V into Y1 plus V into Y2, and we can write this I is equals to V into Y equivalent. I is equals to V into Y equivalent. So what we get from here, that Y equivalent is Y1 plus Y2. So it's Y1 plus Y2, which is equal to G1 plus G2 plus J B2 minus B1. And then you can calculate the current, and if there is interest in anything else, that can also be calculated. So what we see over here, this is an inductive branch. So this current I1, it will lag behind the voltage by some angle. Let's say the magnitude of phi I is coming out to be I1 angle phi 1, and I2 is I2 angle phi 2. Since first branch is inductive branch, current will lag behind, so this will be minus phi 1. Second branch is RC branch, so this current will lead the voltage, so this angle will be plus phi 2. So now we can draw the phasor diagram. For this, voltage will be reference, current I1, it will lag behind the voltage by angle phi 1. I2 will lead the voltage by angle phi 2. Now depending upon the magnitudes of I1 and I2 as well as on phi 1 and phi 2, we can have the resultant current either lagging or leading the voltage. Now, and the expressions for power, whether it's active power or reactive power or apparent power, they are same as we had in case of series circuit. So if you want to write active power, it will be VI cos phi, Q is VI sin phi, and S is V into I, where phi is the angle between resultant current and resultant voltage. So based on this, let's take an example. In this, what we had two impedances Z1 and Z2. They are connected in parallel across a single phase 230 volt 50 hertz supply. Calculate current drawn by each branch, means I1 and I2, total current, phasor sum of I1 and I2, overall power factor, that is the angle, cos of angle with the I, and also we need to draw the phasor diagram. So let's calculate I1 first. So I1 will be equal to, or we can say, let's write what is given. Z1 is 30 angle 45 degree ohms. Z2 is 45 angle 30 degree ohms. Frequency is 50 hertz, though we don't need to use it. Voltage is 230 volts, or we can write this one as 230 angle 0, or you can simply write 230, because this is going to be a reference. We can even draw the circuit. Both the angles are plus, so it means both are RL branches. This one is connected across a 230 volt source, 30 angle 45 and 45 angle 30 degree. So if you want to calculate I1, I2 and I1 will be V upon Z1. V is 230 angle 0, Z1 is 30 angle 45. Now you can use the complex mode of calculator to find it out. 230 divided by 30 is 7.67. This angle will get subtracted, minus 45. This is the value of I1. Similarly, I2 is V upon Z2. V is 230 angle 0, Z2 is 45 angle 30 degree. I2 is 5.11, angle is minus 30 degree amperes. We have to find out the total current I, which is phasor sum of I1 and I2. So I1 is 7.67, angle minus 45 plus 5.11 angle minus 30. Now using the complex mode of calculator, we can have the answer of this I as 12.675 angle minus 39.01 degree amperes. So this is actually value of 5 minus indicates that this current is lagging behind the voltage by 39.01 degrees. We had to calculate the power factor as well. Power factor is cos phi. So cos of minus 39.01 is 0.777 lagging. You always need to mention whether power factor is lagging already. And at the end we had to draw the phasor diagram as well. So if you want to draw the phasor diagram, voltage V is taken as reference, then I1, it's lagging behind the voltage by 45 degree. I1 and this angle is 45. I2 is lagging behind this voltage by 30 degree and also I2 is lesser in magnitude. I2 and this angle is 30. Resultant of I1 and I2 is I, which is at angle 39.01 degrees from the voltage. So this is how we solve the problems of parallel circuit. So I think this is sufficient for this video. In the next video, I will take some more problems of the parallel circuits to have the better understanding of this. Thanks for watching the video.